Hello everyone, welcome to the lecture series on Foundations of Deep Learning Concepts and Applications. In the previous session, we had seen encoder part of variational autoencoder, and today we will look into the decoder part. So, in the previous session, we have seen the working mechanism up till this part. Now, today we will continue the remaining. So, once the mu and variance, once the mean and variance of q, this particular q of z given x, if this is learned by the encoder, then what does it mean? When an input is passed to an encoder, encoder is going to learn the mean and variance of what? Of this particular distribution q of z given x. So, once this mean and variance are learned, the next step is we have to sample z. Now, how is that we are going to get this z? Z is a latent variable and this z is sampled. So, z is sampled from this particular distribution. And what is the characteristic of this distribution? It is having the mean and then the variance. Now, the important question here is how are we going to sample it? What do you mean by sampling? Sampling is randomly picking one number from this Gaussian distribution. So far the input is passed to an encoder and the encoder is going to give us the mean and then the variance of this particular distribution. So, once we have this mean and variance, the next step is we have to get z. How is that z we are obtaining? Z is sampled from this normal distribution. So, we have a distribution which is having the property mean and variance. So, therefore, can we say that z is randomly drawn here? Yes, the latent variable z is randomly drawn. Now, once we have z, what is the next step? The z will be given to a decoder, right? Z has to be passed to a decoder. So, the next step is given z, the decoder models the decoder distribution. What is the decoder distribution? At encoder, if it is q of z given x, at a decoder it is p of x given z. So, at the decoder models the decoder distribution. Now, what is the role of a decoder? Decoder has to reconstruct the data back because VAE is a generative model, decoder has to reconstruct. Now, and at the same time decoder has to give us an output. So, what is that? A decoder is going to give us the output. So, decoder is a neural network which takes z as the input and it is going to output the parameters of distribution. Now, the role of decoder is this. So, it is going to give the parameters of this particular distribution. Now, what are those parameters? So, now, ultimately the aim of a decoder is to reconstruct the data. Now, suppose if the decoder is, it always depends on type of data that the decoder is reconstructing. Suppose if the decoder is reconstructing the continuous data, which means it can be your tabulated data or it can be an images where the pixel values are between 0 to 255. When you normalize, it will be between 0 to 1. So, if at all if decoder aim is to reconstruct the continuous data, then decoder is going to give us this output. It is going to give us the mean and then the variance. Often variance is set to 1 or to a small value. Therefore, the decoder is going to give us the mean value. Now, if decoder is reconstructing the continuous data, then the loss function that we will be using here is mean square error, MSE loss. So, what is the ultimate aim here? The decoder predicts the most likely the pixel value. So, this is the ultimate aim of a decoder. So, suppose if a decoder is constructing the binary data where the data is in terms of 0 and 1, or if it is generating an image, the pixel values are either 0 or 1, then the decoder is going to output the probability. it is going to give us the Bernoulli, it is going to follow the Bernoulli distribution, and it is going to output this probability. And if this is the case, what is the loss function that the decoder or we will be using for this entire, we will be using the binary cross entropy loss. So ultimately here, what is the aim of a decoder? It has to predict the probability that each pixel, whether the pixel value is on or off. So in short, in case if it is too heavy to understand, it is very, very simple. There is an let's say rise and then summarize. We have an input. Input is passed to an encoder, and the encoder aim is to give the mean and then the variance. Once the mean and the variance is obtained, then the next step is Z is sampled from this distribution. What is the meaning of sampled? It is randomly picking one number from this particular distribution. Then Z is given to a decoder. The aim of a decoder is to reconstruct. Now, what are the possibilities that the decoder can reconstruct? Either it can give us the continuous data or it can give us the binary data. Suppose if a decoder aim is to reconstruct the continuous data, then a decoder is going to output the mean value. If the decoder aim is to reconstruct the binary data, then a decoder is going to give us this output. Then what is the loss function that we will be using? For a continuous, the loss function is MSE. For an binary, the loss function is binary cross entropy. So this is all what we are going to do in the training. The input is passed to an encoder, and the encoder is going to give us the mean and then the variance. Once we have the mean and the variance, Z is sampled from this distribution, that is randomly picking a number from this distribution. Decoder takes this Z as an input, and it is going to give us the output, that is the distribution parameters of this P of x given Z. Now this can be either the mean value or it can be the probability value. That depends on what kind of data that is being reconstructed. And towards the end, we compute the loss between the input and the decoder mean. So this is what will happen during training. Next, decoder always outputs the parameters of distribution P of x given Z, but the final reconstructed data points is always obtained by sampling from this distribution. Theoretically, we say that we are sampling from this distribution, but in practical, whatever is the mean that the decoder is giving us, the mean is often used as a reconstruction. I know this particular statement is little difficult to understand. However, towards the end of this, we are going to solve a numerical problem from end to end, so that you will be able to get the complete picture of the working mechanism of VAE. Now, what is the goal here? The goal is reconstructing the data, and whatever the reconstructed data that we have, that we obtain from decoder, that reconstructed data should be as close as the original input x. This closeness is often measured by log likelihood. So this portion is an encoder, and this is decoder. So we are going to measure how close this by using a log likelihood. So with this, we will see what is the loss function of VAE. So there are two terms for the loss function. The very first term we have an reconstruction, and the next is a regularization term. So in the reconstruction, so here we will be using a mean square error if it is an continuous data, or we will be using an binary cross entropy if at all if we are giving an constructing an binary data. So here if you see, we have a negative term or a negative sign. Why is that there is a negative sign? This first term we say that it is a log likelihood. Yes, it is a log likelihood, and we always expect the model to assign the high probability to the observed data. What do you mean by high probability here? So that the difference between reconstructed and then the original input value should be very small. So we always expect the high probability to the observed data as close as the original data. So in reality it is a max of this, but neural network is often trained to minimize the loss, not the maximization. So therefore something which is in a max of a function, if you want to convert it into minimization, it is a negative sign. Therefore we are seeing that there is a negative sign to the log likelihood term. Second, we have a KL divergence. Now what exactly is this KL divergence? Now if you have observed in a variational autoencoder, at the encoder distribution is Q of Z given X. And why we have made an assumption here, and for this assumption, what is the reference that we have taken? We have taken the reference as the latent variable distribution P of Z is a normal distribution. This is the assumption that we had made, and that is the reference for this Q of Z given X. So what does this KL divergence does? It always forces the encoder latent space to match to this reference distribution. So because of this, we are using a regularization term, and here we have two distributions. Both the distributions are normal distributions only. This is whose mean is 0 and 1. And here this mean and variance is something which the encoder has to learn. So in a closed form, this is what is the representation. So here the values can be anything. So here we have come down, we are writing the same in this particular form, so that we can substitute the values and then get one number. So this is what is the loss function of VAE, where the first term can be a mean square error, or it can be a binary cross entropy term, where this is mainly focusing on how well the reconstruction is. And the second term is a regularization term, which is ensuring that two distributions are as close as possible. There is one limitation here. What is that limitation? If you look into this part, into this loss function, here we are going to have a Z term. And how is that we are going to get this Z? Z is a it is randomly drawn from this particular distribution. Now what exactly is the problem if we are going to randomly draw this sampling, since sampling is a random operation. Now once we calculate the loss, we have to back propagate to update the weights. That is, we are using a back propagation algorithm or a gradient descent to back propagate to update the weights. Now here when we are back propagating, when we are computing the gradients, because of this randomness, we cannot compute the gradients here. So randomness often breaks the gradient flow, so making the back propagation impossible. Therefore, how is that we are going to solve this particular problem? We compute the gradients by slightly modifying this architecture. So this leads to reparameterization trick, which will be our point of discussion for the next session. So this is what is the loss function, and because in VAE Z is sampled from this distribution, back propagation does not flow. Therefore, Z is not directly sampled from this. We are going to do a small modification that we will see in the next session. So, this is actually the overall working mechanism of VAE. Since there is lot of terminologies that are included here, let us take one numerical example and then solve or understand in detail the working mechanism of VAE. So, what is the first step? Of course, we require an input. So, here let us assume the input is this data. This is the input. So, and we are having a hidden layer. So, can we say, can we draw a neural network like this? Initially, you are passing 4 features, which is 5.1, 3.5, 1.4, 0.2. That is passed to an first hidden layer. Let us assume the first hidden layer is having 3 neurons. So, if the first hidden layer is having 3 neurons, so let us take another one. Okay. So, we have to now establish the connection. How is that we establish a connection? From here you will have a connection here. If there is a connection, there will be a weight. From here you will have a connection, from here there is a connection, and from here there is a connection. Now, whenever there is a connection, we will have weights associated with it. What are the weights? Can you see? These are the first set of weights, which means we have 0.1 here, 0.4, then we have minus 0.7 and here 0.2. For a simplicity, since our aim here is to understand the working mechanism, so for simplicity here all the activation functions that we are using are a linear activation function. Why is that? Just only for simple understanding purpose. So, now here you will have a summation part and you will have an activation. This activation is linear activation. Once again I am saying this is only for calculation purpose, we are using linear activation function. So, this is the first hidden layer H1. So, how is that we will be writing H1? Can we write H1 as 5.1 multiplied with its weight? Then we have a second input 3.5 multiplied with its weight, the third input 1.4 multiplied with its weight 0.7 and the fourth input 0.2 multiplied with its weight, and we will have a bias term. So, that bias value here what we have taken is 0.1. So, do the calculation and then get the result of this. So, you will see the result will be something this way. So, you can see this is the calculation. So, we had an we have an input. From input we have reached to an hidden layer and you have established a connection. This is at H1 and at H2 this is the connection that you will be doing, right. And what are the weights here? The weights are, these are the weights. And for the H3 we will establish a connection and then there will be a weights associated and those are these set of weights. So, this is what is the calculation that we are doing H1, H2, H3. I hope this is clear. A simple feed forward and we have used a dense layer. So, this is back your week 1, week 2 session calculation. So, we have done H1, H2, H3 calculation. So, once it is done, we have obtained the values. So, these are the output of the first hidden layer. Now, then we have let us assume we have the second hidden layer where we have 2 neurons. So, why? Because ultimately next is the latent space. Always the last layer will give us the latent, whatever is the last layer, the output of that will be our latent space. So, here of course, because we are doing VAE, we are going to sample it. So, let us assume that the second hidden layer has 2 neurons. So, how is that we are going to do this calculation? You see, whatever is the x, that is that x is passed to an neuron which to a layer which is having a 3. Here in our calculation we have used linear activation function, and then we have obtained h. These are the h values that we have obtained. So, what is the next step? We have to get the mean and then variance. So, how is that we get the mean? This h is now passed to an layer. So, you see the hidden layer or the latent dimension here is having size 2. Because the latent dimension is having a size 2, now we will be getting the mean and variance. So, how is that we have to calculate the mean? Now, in order to calculate the mean, here again you are establishing a connection. To this you will be establishing a connection. So, we require weights here. Let us assume these are the weights at this particular for this particular calculation, and then the bias here also we will be adding the bias term, and the bias value for simplicity again we have taken bias as 0. So, what is the calculation? A simple, again we are in the feed forward only. So, how is that we are doing a calculation? H is getting multiplied with its weights and then the bias term. Bias values are 0. These are the weights that we are considering. So, this is the calculation. So, H output H1 getting multiplied with its weight, that is 0.5, and then H2 that is 1.93 getting multiplied with its weight, and then H3 0.87 getting multiplied with its weight plus bias term. So, since there are 2, you will have mu1, mu2. So, mu1 or mean 1 and mean 2 is what we have calculated. This is the values that we have obtained. Next, what is the next step? We have calculated the mean. Now, we have to get the variance also. So, how is that you will be calculating the variance? Now, we require variance and you require variance here. 1 and 2. So, how is that we will be doing? So, again whatever the h value that we have obtained, that h is passed to an dense layer. So, which means here again there are a different set of weights. So, let us assume these are the weights that we are considering, and this is the bias. So, once again we have h values, these are the h values that we have, and these are the weights. Do a simple calculation. So, it is h1 multiplied with its weight, then h2 multiplied with this weight, and h3 multiplied with this weight, and then the bias term. So, this is what is the mean and then the variance that we have obtained. So, what are we doing? We are taking one numerical example, and then we are understanding how the encoder is working. So, here towards the end, so this is the architecture. So, towards the end of this, have we not obtained mean and then variance? So, here towards the end, have we not obtained mean and then variance? Yes, we have obtained this. So, this is the end of an encoder. So, once we get this encoder, once we get the mean and variance, what is the next step? The next step is we have to sample Z. Z has to be sampled from this mean and variance. So, what we are doing? We are just converting what we have calculated is log variance. So, now we are converting that into variance and standard deviation. So, since we have a log variance, so we are now obtaining the variance. How is that? E to the power of, and the standard deviation is under root variance. So, just substitute the values, we are getting the standard deviation values. These are the standard deviation values that we have obtained. Now, what is the next step? So, encoder we have completed, input we have passed, and then towards the end of the encoder we have obtained mean and variance. for simplicity, we have converted it into a standard deviation. The next step is we have to sample Z. So, from where are we sampling the Z? Z is sampled from this distribution. So, whatever is the mean and variance we have obtained, from that we are going to sample this Z. So, which means we have this mean and variance, we have this mean and variance. So, from this we are going to sample the Z. So, let us assume sample is a random operation. Randomly we will pick one value from this distribution. From these distribution we pick one value. So, let us assume this is the Z1 value that we have obtained, and this is the Z2 value that we have obtained. And how did we get this? It is an randomly we have picked one number from this distribution. Okay. Now, the question here is, since Z is sampled from this distribution and this Q of Z given X is a distribution, there exist infinite such Z's. You can sample any number of Z from this. Now, again you can randomly pick one more number. So, initially from this given obtained mean and variance, when we have sampled Z, we have obtained this value. Again, can I randomly pick one more value from this distribution? Answer is yes, you can pick a value. One more time you can pick one, randomly you can pick one more number, this is the value. So, you can pick any number of Z from this particular distribution. So, this is one important point you need to remember. So, let us continue with our calculation. So far what did we do? We have taken the input, we have passed it to, we have obtained the mean and variance. From that mean and variance we have picked one Z, and let us assume that the Z value is this. Now, ultimately decoder has to reconstruct the data. So, which means decoder is a neural network. What kind of neural network? So, here we are passing two values as an input, and from here it is 3 neurons at an hidden layer, and at an output layer, since you input what you had taken was 4 features, the output also should have the same dimension. So, this is the neural network that we are going to build now. So, this is what is the neural network, and so on and so forth. This is the decoder part. So, because there are so many number of connections, every connection will have a weight. So, now let us assume the first we are doing this part of the calculation. So, these are the weights that we have assumed here. Okay, and there is a bias term, and the bias value here is this. So, how is that we do the calculation? So, you see the calculation is Z multiplied with the weight plus bias. So, what is Z? Z are these values and these are the weights. So, the first 0.041 multiplied with this weight, then second 0.486 multiplied by this weight plus bias term, we are getting this. Next, we have the second feature. So, we have 0.041 getting multiplied by this, and then we have this getting multiplied with this weight. And we have the third neuron. So, again you are passing this input getting multiplied with this weight, and this input getting multiplied by this weight, and then the bias term. So, it is a simple feed forward calculation which you are very much familiarized from our earlier weeks. So, with this we are now getting these H values. So, we have since there are 3 neurons at an hidden layer, we have obtained 3 values. So, here again for simplicity the activation function used is linear activation function. So, next we have these many number of, now we need to do this calculation. So, to do that calculation, these are the since there are 4 neurons, we have 4 such weights that we are assuming. and do a calculation. This is the calculation that you will be doing. Now H gets multiplied with the weight and then the bias. So these are the calculations. So how is that you will do? First H1 getting multiplied by this weight, then H2 getting multiplied by this weight, and H3 getting multiplied by this weight plus bias term. For simplicity, the bias what is taken is 0, 0. Yeah. So, since the bias is 0, we have not written, otherwise it is 0.0. So, you do this calculation, you will get these numbers. You will obtain these 4. Now, where is that we have reached? From this hidden layer we have reached to this output layer. So, we are doing a decoder part, and what is that? Decoder is trying to reconstruct the data. The decoder is trying to reconstruct the continuous data. What is continuous data? Is it not a continuous number here? Now, because it is a continuous number, so theoretically what does it says? The decoder distribution is P of x given z, and here it is giving us the mean as an output. Right, from the previous slide we have seen decoder is going to give this mean as an output. So now what is that mean? So this is a reconstructed data, and we call this as a mean also. So theoretically, although theoretically we say that we are going to sample from this distribution, but practically whatever is the value that you have obtained, that itself is considered as a mean, and that is the reconstructed value. Now, you can ask the question, the original input what we have considered is 5.1, 3.5, but what we have obtained the reconstructed reconstructed data, there is no match at all. Yes, there is no match because it is first iteration, first epoch that we are doing it. So it is the first time you have done the forward pass. Then you will compute the loss. Based on the loss, you will back propagate, you will update the weights. After once the training is done, you will see that the reconstructed data will be as close as the original one. So whatever the mean value that we have obtained, this is or the reconstructed, this is actually the mean of this particular distribution. So what is that we are seeing? The decoder is always going to output the probability of x given z. So this will return the mean if it is an continuous data. So whatever the output that we have obtained, that is the mean from the decoder part. So what does theoretically it says? Theoretically we say that whatever x that you want to reconstruct is sampled from this distribution, but practically whatever is the mean value that you have obtained, that itself is the reconstructed data. So for our numerical example, this is the reconstructed data, this is the original input that we have obtained. If you see, there is a huge difference between original input and then the reconstructed one. Why? Because we have still not completed the training. So once the training is done, all the learnable parameters are optimized, then you will see that these values will be as close as this original input. Yes. So the next is calculating the loss. So how is that you will calculate the loss? Because you have to back propagate, right? So how is that you will calculate the loss? Because it is a mean continuous data, what loss that we are taking here is mean square error loss. So from theory we have seen that it will calculate the loss is calculated between the original input and then the mean value. So substitute the values, the original values are here, and then this is the mean value. Just substitute the values and then you will get this term, this value 9.8509. Now what we have calculated in the loss function, we have two terms. The first term is the reconstructed one, so we have seen the reconstruction loss, but second term is KL divergence, right? So, if you remember the KL divergence, this is the formula for KL divergence. So, from where do we get all these values? These are all your encoder output. So, encoder is going to give us the mean and the variance. So, get the mean value, and we have calculated a log variance. From here you get the variance value. So, substitute the values in this particular formula, so that we get KL divergence value as this term, this value 0.352. How is that we have calculated? Since there are two mean, so you will have two terms here. So, 1 by 2, it is I, we can take it as I, and then it is a summation term. Therefore, we will see first when I is equal to 1, we will have a mean 1, mean this is first value. So, and then you are taking a square of it, so you have obtained this. And this is the variance, so you are taking this value, and this is minus log of, so you will take this value minus 1. So, since you have the second set of values, for the second set of values it is this. So, substitute the values in this formula, and then finally you will see the KL divergence value is so much. What is the total loss? Is it not the total loss is the addition of both the terms? Therefore, this is the loss that we have obtained. It is such a huge loss. What is the next step? With this loss, we have to back propagate. Now, when we have to back propagate, you will compute the gradients, and you will see that when it reaches to Z, which is sampled from Q, when it reaches to this, the gradients does not flow. Therefore, this leads to reparameterization trick. After once we see the next session, you will see what is the actual architecture of VAE. Of course, this is the actual architecture, but Z is not directly sampled from this. We do a slight modification how we are going to generate this, or how we get this Z. Once we have the mean and the variance, Z is sampled from that distribution. So, when Z is sampled from a given distribution, this is the first time when you have randomly picked one number, this is the value. This value, when you passed it to a decoder has given this. This is what is the calculation that we have seen. Now, can you pick one more Z from that distribution? Yes, answer is yes. So, we will get this as randomly you have picked, and this is the Z we have obtained. When this Z is passed to a decoder, is it not we get one more reconstructed data? Now, when you take this Z, when you pass it to decoder, we will get one more reconstructed one. So, which means each Z that is randomly sampled generates in a different distribution. First, it generates a different distribution. From this, you will have a different values. Yes. Now, the question is, which latent variable Z has produced the data? Because more or less all of these Z's will give us a same data. Now, which Z has produced this observed data X? So, what is the answer? So, the answer is P of X is obtained by summing up all, by doing the summation of all the contributions from all possible latent variables. So, whichever latent variable Z is closely matching to our original input. So, it is a summation of all those Z's which has actually produced this observed data. Therefore, You remember there is a question which we have asked, why P of x is so hard to compute. Sometime back I have said P of z, no, it is a P of x. Why it is so hard to compute? Because there are infinite such z's that are possible, and every z produce a different P of x given z, and there is no closed form solution because integral we are using. For an integral there is no proper closed form solution. Therefore, calculating P of x is very hard. So, because of this, what exactly we had started? We wanted to calculate the true posterior P of z given x, and using a Bayesian rule, this is what. And if you remember, when we had seen the encoder part, P of x calculation is very hard. So, why P of x calculation is hard? This is the answer. So, here infinite such z are possible. When infinite such z's are possible, every z is going to give us the different distribution. And if you ask which is which z has produced the x, it is the summation of all of those. Because of this, because P of x is hard to compute, we will not directly use P of z given x, we will not directly compute P of z given x. Therefore, we have introduced the approximation Q of z given x. So, encoder is going to learn this. So, this is all about the working mechanism of variational autoencoder. We have in the last session we have started with VAE. We have seen the encoder part in the last session. In this particular session we are seeing the decoder part. For a better understanding, we have taken one numerical example, and then we have solved the encoder and then the decoder part. Now, in the next session, we will be seeing the most important called reparameterization trick. And what does the reparameterization trick says? So, this is what is z. So, z is randomly sampled from the distribution. Z is randomly sampled from the distribution. So, now instead of doing this, z is taking this particular form. This is the reparameterization trick. Z is going to take this form. Because z is going to take this form, after you understand the next session, come back to this session and then once again see how Z1 and Z2 is calculated. Z1 is calculated by this particular formula, because we have already obtained mean and variance. From our calculation we have obtained. So, rather than randomly picking Z is taking from this particular formula. Substitute the values in this, you will understand what is this term, and then you will get this z. With this z, once again do the calculation. So, in the next session we will see only reparameterization trick. After you understand the reparameterization trick, come back to this particular example and solve by taking z and then compute the decoder part. Thank you.